Welcome, everybody. Happy Thursday, and thanks for joining us for another Coffee with Caleffi. I'm joined by Bob Rohr, and today we're going to talk about expansion tanks. And you might be a little confused because at Caleffi we do not make expansion tanks, but they are a vital part of every hydronic system as well as plumbing systems. And today Bob and I are going to kind of give you the ins and outs of them and answer any burning questions you might have. And but before we get into the meat and potatoes, we're going to go through some of the housekeeping slides here. Alrighty, so if you're having any issues with audio, which we actually just got a question about audio, if you're having any issues, make sure that you log out and log back in. If you continue to have issues, definitely check in with the technical support through GoToWebinar, which that's not our tech support, that's their tech support. And if you're looking for a copy of today's presentation, there is going to be a survey at the end of the webinar. You click yes on that request there, we will send you a copy of today's webinar. And if you can't make it through the whole webinar today, or you're hoping to share it with a colleague or anything like that, we record all of these webinars and put them up on YouTube roughly within about a week or so, and you can check it out there. So, alrighty. And for those that do attend today live, we are going to send out a certificate of attendance. If you can use that towards any professional development hours, that's fantastic. So check that out in your email. And then from there, you know, just some quick little shameless plugs here. We were an Innovation Award winner, or award finalist, excuse me, for the 2022 AHR for our trifecta of products here for domestic hot water control, including our Legio mix, our sink mixer, and our thermal balancing valves, the thermosetters there. So definitely check that out if you're unfamiliar with them. And we try to plug this on every single webinar, our Hydronics journals. They're a great technical journal, very, very, very useful for everybody. And our most recent version, or our most recent issue, is going to be on pressure reducing valves. So check that out as well. And then too, we also have a digital version that's available at hydronics.caleffi.com, which gives you all the same content as far as what's in the actual Hydronics journals, but it actually gives you added content as well. It'll link towards videos and things like that. That will help basically kind of coincide with the Hydronics journals that you're reading. So check that out as well. And next month, it's going to be myself and my colleague Dan Furcus, and we're going to be talking about electronic mixing valves in domestic hot water systems. So if you're getting into those electronic mixing valves and you're seeing more of them and you're kind of swaying away from thermostatic mixing valves, this might be the webinar for you, because we're going to talk about just kind of how to go about working with an electronic mixing valve, installation, operation, troubleshooting, just some pitfalls to watch out for and things like that. And again, Dan and I will be taking care of that next month in September, so make sure to save the date for that one. And now we get to introduce ourselves, Bob. All right, well, thanks for coming on board here with us and everything like that. Bob and I, like I said, we're going to talk about expansion tanks, and I'll leave it to you here, Bob.
Yeah, thanks everybody for tuning in today, and also thanks for the excellent pre-submitted questions, we call them, because it forced me to go and learn a few new things too. I had to research some of those questions and come up with some answers, and there's a few I'm not quite sure on, so hopefully the Amtrol people or some of the tank people that are tuned in today might be able to help us out on that. So yeah, these are the topics. I think you probably saw these on the teasers that went out. We're going to try and cover quite a bit. You know, when I first put this together, I thought, yeah, what am I going to talk about for 55 minutes? And I got into it, and by the time I looked at, you know, solar and chilled water and everything else, it got pretty big. I wish we had 90 minutes, so we'll move through it quickly. We'll try and cover, like I say, potable water applications, a little bit of solar and chilled water, and throw it all at you. Yeah, and here's some places that some of the slides that we'll show today came right out of these manuals. Of course, the Caleffi Hydronics, we talk about expansion and contraction on chilled water systems and a couple different issues. And that Amtrol engineering handbook is kind of my go-to, and I have a question on system, especially on a compression tank system, on sizing and pipe sizing and stuff. And I think it's available online still. It's last updated in 2011. I think that is the most current one. If you have an Amtrol rep, sometimes they have a stash of those, but a lot of, I mean, if you're the math and number crunching guy, there's formulas in there that'll take it to the end of time, but it's pretty
Make
interesting.
my head spin. Yeah, but they do still have that as a PDF right from their website. I was able to download that some time ago. It's a big PDF, so check that out.
Yeah. Yeah, so basically what we're going to talk about is we heat up a fluid, water, or maybe a glycol mix. It's going to expand, and the opposite happens if we chill down a fluid, it's going to contract. So we need to be able in a closed sealed system be able to accommodate that somehow, so we don't pop relief valves. On the other side, if we go into a negative pressure condition, we can cavitate our pump. So we're going to look at the vessels that can be used to do that. We're going to look at a completely open system like they still do in places with just a bucket up in your attic that's insulated as an open system, and the pros and cons of all these different types of tanks, and how to size them, and troubleshooting a little bit also. Okay. Yeah, so I'm not going to read through this. If you get the slides at the end, you can read through some of these kind of wordy slides, but this came out of one of our hydronics. And basically what we're saying here is you can't squeeze water or fluids, at least under the pressures that we're familiar with working with. And this is one of the things I was forced to look up, I guess. To squeeze water by 1%, it would take 200 times atmospheric, so 14.7 times 200 times, you could compress water 1%. So obviously that's a big pressure number, not something you're going to typically see in a system that we're working with residential, even small commercials. And if you wanted to get to near 100% compression, it would take 2 giga, what do we call them, gigarascals or gigapascals over there in Europe or something.
That sounds good.
If you want to figure out what 2 gigapascals are, that's the kind of pressure we're talking about. So we're going to talk about how we can accept that expansion as the water heats up and contracts. And here's probably two of the most common systems that you're going to come across out there. One on the left there is called a compression tank, or sometimes called a plain steel tank. And it is that. It's just a tank that has some water and some air in it. And they're still around. You can still buy these tanks. They're getting pretty pricey these days. And that is what's called an air control system. And what we mean by that is that little air bubble that we're kind of indicating there as a red in that picture needs to stay in there. We got to control or manage that air bubble because that's our expansion. If that goes away and the tank becomes waterlogged, then we lose the ability to have expansion space, and we're going to pop a relief valve. So you got to pipe those properly. There's a couple little valves that they've added into these that you can make them work a little bit better so they don't, thermal siphon all your heat out of your boiler. On the right, I'm not sure exactly what to call this. I guess the official name would be a pneumatic.
Hydropneumatic.
So thanks, Cody. You've got both water and air, and the big difference there is that we're separating. We physically have a bladder, a diaphragm, a bag, a tank. We've got something in there that physically separates the air from the water. So that does a number of unique things for us that we'll go through as we look at the different tanks. So in this air management system, you can see what happens over there. So what I found out in my research, that if you're going to fill a system at 12 PSI, what's going to happen if you fill that tank up, let's say it's a 30-gallon tank, at 12 PSI fill pressure, it's going to take about 44% of that tank is going to fill up with water before you squeeze that air bubble at the top of that. So as a result, your tank needs to be much bigger to handle that expansion. And now you've added, 44% of 30 gallons, you've added that much more water to your system that, of course, you got to accommodate the expansion of that also. And if the tank gets warm up there, you've got a little bit of a radiator up there. So that's, some of the, I don't want to say downsides, but that's some of the, things that you want to be concerned about. And of course, we don't want to put any kind of air elimination device on this type of system because we don't want that air, which is going to go in and out of solution. In the summer, when the boiler's off, that air that's in that bubble can be reabsorbed into that water. And then if you come and you start venting radiators at the next heating season, you're going to vent away your air bubble. So on the very far right there's a couple manufacturers that make a couple fittings that made these tanks work or behave a little bit better. So basically what we want to do is, as we take the air out of the top of the boiler there, the hot part of the boiler, we want to shove that air bubble up into the top of the tank. So that little fitting there is going to have a little tube in it that'll take the air bubble out there, and that'll also prevent it from thermal siphoning, because we don't want the heat from the boiler going up to the tank and just warming up that tank, because then, like I said, we're just losing some heat through the wall of the tank. Now, you could insulate the tank, and people have done that, but when you insulate it, you drive the operating temperature of the tank up. Now your tank has to be bigger because you got to accommodate more expansion. So you're kind of like a dog chasing its tail when you try and improve on this basic plain steel or compression tank. And they'll have a sight glass typically on the end in the middle picture there, so you can see where your air bubble is, and you know if your tank's getting waterlogged that it's time to get the air bubble back in there. Either pump some air into it, drain it out, refill it again, and squeeze your bubble back in there. The tricky part is if anywhere in the system you have a little air leak around the valve packing or something like that, you can lose your airspace out of there. So yeah, you want to keep the air in.
And I'll mention too, compression tanks are really awesome for those of us that are over 6 feet tall in basements as well. They're a great place to crack your head on. Bob, you mentioned it earlier about air elimination. You put an air separator or an air elimination device in your system, and that's a great way to get rid of that air bubble that's going to be in that compression tank, waterlog it, and then start popping pressure reliefs. And it's definitely something you need to be aware of. And I would say, similar to this boiler fitting that you talked about before, air scoops, I think those are probably better suited towards air management as opposed to the top of an air scoop, putting an air vent on there. Having a pipe that goes up to this compression tank up there is going to be the best way to manage the air and keep that air bubble in there and prevent it from waterlogging.
We actually, for our disco air separators, we make a little fitting that you could put a tube on it, and you could take the discharge of that air vent and take it up there. So any air vent that you do that does come out through the disc valve would go up into the tank. So if you do want to put an air elimination device on that type of system, just get the air back up into the tank, just don't vent it. Sure. Got it?
Yeah, right. Got it.
Yeah, I got a picture. I guess this goes back to when these tanks were first invented, but you can see that you gotta have a 6-foot helper there to put one of these, and that's a small tank. You're probably looking at maybe a 30-gallon tank there. If you start getting the bigger tanks, obviously, you could either, mount it on the floor, mount it somewhere else. Yeah, you got to put it somewhere. All right, so air elimination. So this is probably the more common system these days. If we have high efficiency boilers and we've got high efficiency heat emitters, don't we want to get all the air out, and don't we want to get it out quickly, and don't we want to get all the way down to a micro bubble size so we don't overheat our heat exchangers on a ModCom boiler, for example, where we only got a gallon of water in that heat exchanger, we got 350-degree flame temperature. We certainly don't want air bubbles in there. So these micro bubble resorbers, like you see the Caleffi disc scale that we just talked about on the top, they're going to get 97% of the air out of your system within the first couple hours. As long as all the fluid is going past that device, you're going to grab it, whether it's hot, whether it's cold, whether it's big, whether it's small. So that's really the best way to get the system evacuated quickly, efficiently. We show a little fill valve there on the right, because as we're taking air out of the system for the first couple of days, perhaps we got to put water in behind it, or we're going to lose the pressure in our boiler and maybe go into a low water cutoff condition. So we want to fill water as we vent air out, and we want to get that air out at the hottest point in the system. In this picture here, you can see we've got it right at the top of the boiler there. That's where the air is going to come out of solution best. And now, we're going to talk about this, Cody. I don't know on this slide, maybe a lot. The expansion tank doesn't need to be on the bottom of the air separator. You see it there all the time, and Cody's got some thoughts on why you wouldn't necessarily want to put it there, or put it there like it shows in that picture. And I'm going to let you elaborate on that.
Yeah, no, take a breather there, Bob. Yeah, with the air separators, they all have a 1/2 inch, especially on like the smaller residential size ones, they have a 1/2 inch tapping on the bottom of them. That's perfect for adding an air separator an expansion tank. And, ideally you always want to be pumping away from that expansion tank. You always want to be pumping away from your air separator in order to get, the lower pressures at those points. And that's a great place for your point of no pressure change, which we'll talk about in a second. But, it was brought up to my attention that, you get an air separator in that big wide passageway there, that low velocity zone. It actually acts a little bit like a dirt removal device too. And despite the fact that air separator, the difference there and how shallow it is, I mean, it could still get a little bit of dirt and debris inside those expansion tanks. So just something to think about, instead of putting that expansion tank here, on a low pressure drop type boiler, you could actually take that expansion tank and put it right here, connect it with your fill valve right over here, and it's not going to make that much of a difference. So food for thought, and I always try to keep my expansion tank connections, between like the 3 o'clock and 9 o'clock position on a pipe. So that way nothing falls down in there, but just something for you guys to noodle on there.
Yeah. And then the last point there on that slide, Cody, if you give me a second, there is, sometimes if people oversize the piping, and I'm working with a guy right now in one of the chat rooms that wants to pipe his boiler with 1.25 inch pipe, even though he barely needs 1 inch pipe. I said, well, you're going to slow down the velocity. If you slow down the velocity on these camel type of air scoops don't do a very good job of pulling the air out. Now the micro bubblers like the disc gal will work down even at 2 feet per second velocity. So, you know, that's the difference between just using a wide spot in the road as opposed to having something that has a mesh or median to grab bubbles at slow velocities and also the smallest bubble possible. So
For sure.
okay. Yeah, so now were you, the guy that's putting the system or the girl putting the system together, connects the expansion tank in the system is what establishes the point of no pressure change. We can't stretch water, we can't squeeze water as we just talked about at these pressures. So that's the only point in that little diagram there where I can't change the pressure in the system, and the circulator can't change the pressure in the system at that little point. Now notice there's a little bit of droop in pressure between the tank and the pump because there's a little bit of pipe there, a little bit of pressure drop. But when you pump away from the expansion tank, all the pressure differential that little circulator can add to this loop shows up immediately as an increase in pressure. So if you notice there, we filled at 10 pounds everywhere in that system at that elevation. And as soon as the pump kicked on, we went up to 18 PSI. Now that helps us with air elimination, that makes sure that any vents that we have out, you can see some high point vents maybe in that drawing there, have sufficient pressure so that they can vent properly and also seal off. So if we did the opposite and moved that expansion tank on the other, that pressure differential that little circulator was adding there is going to show up on the other side, and you can actually pull a subatmospheric and negative pressure condition in that system. And what happens then? You've got a vacuum pulling air into your, air vents and your seals around pumps or valve stems or something like that. So pump away from the point of no pressure change. Within a few inches or feet, that expansion tank on the suction side circulators.
All right, so we got a quick question that you guys can throw this in the questions pane there. If you guys have an answer to this one, where should you locate the expansion tank in a hydronic system? We mentioned it a little bit before, but I mean, if you think about it on the supply, on the return, before the boiler, after the boiler, how do you guys do it? We're curious what you guys see on a regular basis and what works best for you. So go ahead and throw those in there. We got one person saying before the boiler. I presume that you're looking for the cooler temperatures there, suction side of the circulator, lowest pressure, highest temp. Yeah, some great answers in here, guys. Yeah, wanted to make sure that you guys were still awake there. So
yeah, and so here's to Cody's point and to the answers that are coming in, classic examples of how you could put the expansion tank, number one, on the cooler fluid side of your system, and also not under the air separator on top, because it's going to leak into the boiler someday if it was hanging under those air separators on those two pictures. They're all going to leak. Just one given about expansion tanks, they're going to fail. They're either going to rust through, diaphragm's going to rupture, the Schrader valve is going to fail. They're all going to leak at some point in its lifetime, I guess you could say. So yeah, so in all these pictures, we've got very low pressure drop between the circulator pumps, so they all are pumping away the point of no pressure change, even though it looks like, gosh, it's a long ways away from the circulator pumps are on the left or on the bottom. But again, on the bottom, we've got a hydro separator in there. We've got large diameter piping. In the center picture, we've got a wide open boiler, cast iron, maybe electric boiler, whatever it might be, very little pressure drop in that boiler. So they could be on that bottom side there.
Yeah, definitely something to think outside the box. Yeah, like Bob said, you don't have to hang it always on the supply side. Obviously, if you were to look at it from this side, you'd put it, on this side of the boiler. If you wanted it on this side of the separator, put it right before that circulator there. But over here, you've got this nice long header, and you're pumping away from it. It just looks a little different because you've got this long header here, this big low velocity zone here, and a little bit of header here. But the pressure drop from one point to the other is pretty minimal.
And notice too that they're all on dead legs, so they're not going to get any dirt and debris that they might hanging under the separator on them too. So now on a chilled water system, here we go. We want that expansion tank in there also because we can, as we cool the water, we can retract. The pressure is going to drop. So the same thing applies to geo. For years, the geo industry said, no, we don't need expansion tanks. The tubing can expand and contract and handle that type of thing. But really, on a chilled water system, there's a good reason to have them there. And yeah, we'll go into that a little bit more in a couple of slides. So I think what I wanted to show there on the bottom right, on this picture, people ask, okay, what size does the pipe need to be between the expansion tank and the wherever you connect it into the system, into the boiler? So You have to get into a pretty big system before you have to start worrying about going beyond a ½ inch. I did a couple in fact, there's an excellent example in the Amtro book, and it's like a 7,000 gallon system running at 260 to 270 degree F. It's pressurized, I think it's 65 pounds or something like that. And yeah, under those conditions, it took an 1.5 inch pipe, because what you have to be able to do is accept the expansion, the 35 gallons that system's going to expand when it goes through that temperature differential through that pipe, without raising the pressure that it could pop the relief valve in the system. So if it did, it turned out to like 10 gallons, 10.7 gallons a minute, has to be able to move through that pipe without causing a restriction that would, have the pressure go up above a relief valve. So the math is about 4 pages long. It gets a little bit complicated. There is in the Amtro book a quick sizer for that also. If you're number crunching, want to know exactly what the pipe size needs to be, you can run it through those acceptance, formulas and come up with that calculation on the pipe. But I think on the quick sizer, it goes up to like 1 million BTU on a typical system. 3/4 would still accommodate that. So if you want to crunch the numbers, you can. If you want to use the quick sizer, there is one in the Amtro handbook. So that was one of the pre-submitted questions about sizing that pipe. And the other one, since we're right here, somebody said, okay, if I do have 30 feet of pipe, and I fill up my system over to the, let's say we got a diaphragm type, do I have to purge the air out of that line? And I asked Siggy and I asked one of the Amtro people, is there a problem if that air is in there? And we're under the opinion, well, eventually that air is going to get absorbed and come out of your air purger if it's trapped in that 30 feet of pipe. If you want, I guess you could loosen the expansion tank and bleed it out as you're filling, or put a Webstone valve on there that has a little purge cock that you can purge from either direction, purge that little air that's trapped in that, 30 feet of pipe or whatever we're showing in that drawing, and purge it out. But unless somebody else has a reason, I don't know that air would be a bad thing or would affect anything and that's trapped as you fill that.
Well, like you said, Bob, like even if that 30 feet of pipe goes up and over and everything, you're going to have trapped air in there. But like you said, if you've got an air elimination device that's properly functioning, that air is going to sooner or later get, absorbed back into the water that's flowing throughout the system, and it'll get out of there sooner or later. But yeah, a good purge valve might not hurt either.
Essentially what happens in a compression tank is that air gets absorbed back into the water, and then if it gets vented out, you lose it. So that's probably what's going to happen to that air. It'll go back as the water cools maybe in the summer and then get vented out. And I just, for the life of me, don't understand why these are still such an item. You can see all the flags are in that picture. This company manufactures, that's just a hinged lid on the top of a square box, I guess. I'm assuming it's stainless steel or something. And this is an open expansion vessel that goes in the high point. You see them in the UK in attics, and they've got all this insulation wrapped around them, and that's your expansion vessel in your attic that, yeah, I don't know, maybe they're inexpensive or something like that. It just seems like, number one, a lot of heat loss up there. Number two, it's going to leak someday, and then it's up in your attic leaking through, your flat of maybe 3 levels. So I don't get it, but they're out there. The other thing is, you've got oxygen in contact with your water. So now you've got the potential to have more rust, corrosion going on if you keep allowing oxygen in the water. And know that the higher the temperature of the fluid, the more the oxygen is going to want to go into that fluid. So if you're running this on a 180 degree system, you got quite a bit of oxygen diffusing in around the lid of that tank. So again, if somebody can sell me on a good reason why I'd want to use an open tank in my attic for my expansion device, I'm listening, but they're out there.
They're also really fun if you don't know they're in the attic and you start pressurizing the system and then it starts raining from the ceiling. That's always a good one. I don't know if anybody's run into that. Feel free to put that one in the questions pane there, because it's definitely something you want to avoid if at all possible. So
I suspect those high taps on that are for that reason. That's an overflow. If somebody overfills it, it goes outside or something.
Yeah.
The other question that comes up a lot, and again, I don't know that I have an exact answer to this, is can I mount a tank other than nipple up under, wherever you're going to mount the expansion tank on a fitting, or like we showed on those previous slides. And this is right out of one of the manufacturer's installation manual, which I did get permission to use. And it says the preferred method is with the nipple up hanging down like you see in the bottom of the center, the first drawing there. It does show an optional location with a nipple down and the tank up. Now what you're going to do there is you're going to trap some warm, moist air above that diaphragm, and maybe that tank doesn't last as long. I've seen them both that way and on their side, like on the left there, for 15, 20 years, and I don't have any example that they don't last as long or anything else. So, you know, if you do mount it on, if you mount it anyway, but especially on its side, make sure that you support it. There in the intro book on the right, they say make a, you know, a trapeze or cradle or something to hang them that can support the weight of that tank if it does, when it does fill with water. And obviously if it's a big multi-100 or 1,000-gallon tank, you got to be able to accommodate the weight of that tank on a mounting, probably on the floor of the building or something like that. So, you know, if you can mount it nipple up, that seems to be the most accepted way of doing it, but know that guys are putting them, and I think I've got some pictures coming up on their sides, and, you know, racking multiple small tanks together instead of buying a big ASME tank or something to save some costs. So.
Yeah, and you know, Bob, you mentioned, you know, how can you justify one way or the other? Is it going to last longer and everything like that? And, you know, honestly, I think especially with expansion tanks and hydronic systems, you know, more than anything, how long they live is more so to do with water quality and oxygen ingress and everything like that versus which way it's mounted. However, I can tell you without a doubt that this up or down kind of mentality here is like a Ford versus Chevy debate. Anywhere I go to talk about it, because everybody swears by one way or the other. But I'll be curious to see if anybody has any comments on that one. But more than anything, you know, make sure that you're supporting the tank. I mean, that's code in just about everywhere. You know, you need to make sure it's supported. You don't want to hang it off of a 1/2-inch copper line. If that tank the diaphragm were to rupture for whatever reason, you know, you need to make sure that you can support that weight of the water. So yeah, obviously you've got some brackets here. I don't know which one, anybody could have a favorite, but you know, as long as you're supporting it, I think you're in good shape.
Yeah, and don't hang them over something that when they leak or if they leak, they're going to drip into the boiler, the electronic Techmar controller, something like that. A number 30 tank, I think, holds 4.4 gallons when it's full. So you've got that times what, 8.3 pounds per gallon. That's a lot of weight.
35 gallons of water, 35 pounds, yeah.
Number 60 is like 10 point some gallons of water. So now you're talking, you know, with the weight of the tank and everything, you could be talking 90 pounds that you got to have more than just a 1/2-inch pipe, copper pipe holding that up. So these are some options out there. There's probably others, but all these work great. Those bars on the left allow you to put a gauge up there. You could put a little bleeder up there if you did want to bleed the air out as you fill it. You got an isolation valve if you want to put your fill valve in there. So that brings a little bit more usability to the mount if you have a bracket that can do multiple functions. You can make your own with, you know, plumber's tape or something. And so, yeah, just to brag a little bit, right behind me, if you can see in the picture, is one I made. I thought, you know, what if I made one out of stainless steel? Just kind of built that, and I made it 3/4 and 1/2, so it could be used for domestic water or hydronic water. Just flip it over, and now you got a 3/4 connection. But you can see I put an air vent on there. I hooked to my system. I got my fill valve off to the one side of it. So it's, again, just an example of a multi-function mounting bracket for an expansion tank, and fill. You could put a relief valve up there too if you wanted.
Yeah, I think this is a good time too, Bob, to bring up, you know, when you are troubleshooting a failed expansion tank. Somebody popped into the questions there and said that they do the tap method on expansion tanks to see if they're all waterlogged and everything like that. I'm going to tell you, I've not had good success with the tap method or the thunk method, as I think it was referred to. Have you had good success with that one, Bob?
Well, limited or mixed result, but now that you brought that up, I think Amtro has had, or they know they do in their new tank, they're coming out with a clear plastic cap, it looks like, that goes on the bottom, and you screw that tight, and it must push the Schrader valve, and it's an indicator. If your bladder's failed, it turns colored. It's rusty, it turns red colored. So I guess that's, you know, in between pushing it in with your finger or wrapping it with your knuckles to see if it's waterlogged or shaking it. Everybody's got a different method to see if it's waterlogged. Obviously, if the pressure goes right up when you fire your boiler, that's another indication. But yeah, I would say, you know, it's the pinholes are probably the most common if you got non-barrier tubing in the system. I've seen tanks within a year start to get little blisters on the paint and a pinhole because they're getting all the oxygen in there. Undersizing your tank where the diaphragm shoved way up beyond its comfort range will shorten the life. And, you know, like Cody said, dirt laying on the diaphragm, so as it moves up and down, the dirt's kind of eroding through it. Those are all, you know, things that can shorten the life of it. You know, it's a thin steel tank. It's not going to be a 100-year product. I mean, let's be realistic on what this tank really is made out of and what it's intended to do.
Yeah, so I mean, if you are looking towards the future and you are looking for serviceability and everything like that, you've got this little valve kind of set up, and you can make this all out of separate components too, but the ability to drain off the water side is going to be ideal. I can't count how many jobs I would see with Extrol 60 tanks on these old gravity conversions and stuff like that, where they just had a valve connected there, and if I knew then what I know now, I'm trying to bear hug this thing and trying to, unthread it. And meanwhile, I'm taking a bath and everything else. Make sure it's supported, make sure you can get the water out of it. You need to get the water pressure out of it in order to test the air side or change it for whatever reason. But another little trick that I learned just over the years is if it is waterlogged and you don't want to deal with the bear hug shower and everything like that, is just run a zip screw in there and then, pull that zip screw out of there and have that water shoot out in whatever direction you want. Put a new tank in there and you're off and running. So
yeah, zip screw is a nice way to go. And notice too on that lower right picture, that's what I call one of the webstone valves, and that's one of them that you can purge from two directions. See the little label on it where it's got arrows both ways? If you flip that handle over, I could purge my air out of that line if that was a concern for me. Then I could turn that handle over, shut it off, and now I can purge out of the tank to drain my tank off if I want to recheck the air charge or replace it. So that's a handy valve where you can work from both directions on your, and it's got a nice hose connection to put a hose on it and take it to a bucket or a drain to drain it off.
Yeah, and I'll bring up too, we get quite a few questions on the tech support calls regarding what they think is a failed fill valve. Like you got a fill valve here for your boiler that's maintaining a set pressure. And if it goes over that, you automatically think, well, maybe it's a bad fill valve. What I would suggest in those scenarios, if you think it's a bad fill valve, I would also consider the expansion tank as well. And what we usually recommend in those cases is, at a cool point or get the system cooled down, set your static pressure, isolate the fill valve, and then fire the boiler up and see what happens. If it starts going up, chances are it's your expansion tank and really nothing to do with your fill valve whatsoever.
All
right.
And that happens to be our high flow fill valve, at 9 GPM valve. So there's the tanks that are on the websites as we speak today that you can buy. So there's your plain steel compression tank on the left. Now in the center, this tank is a little bit different than a diaphragm. This is sometimes called a bag or a bladder type of tank. And what's different about that is you've got pretty much full acceptance on that, because that bladder can, or that bag, whatever you want to call it, can expand to pretty much the size of the tank. So if you look at the diaphragm tank on the right, they really don't want you pushing that diaphragm up against the very top of the tank. In fact, when you put an expansion tank on a system, and if you've got a pre-charge to what your static fill pressure is going to be, that bladder is going to be right up against the nipple at the end of the tank. No water goes into these tanks, which is why they can be sized so much smaller than the compression tank, because the only water that goes in there is the expansion water. I don't have to put water in there to trap an air bubble like I do on the plain steel tank. So usually a half to a third the size of a compression tank is what you're going to have on one of these tanks. Now the one in the middle, some of those you can pull that, I don't know if anybody's ever done that, but you can pull that bag out and replace it if it ever went bad. There are some partial, there used to be, I don't know if there still were, I know when Jody did this for us about 10 years ago, there were some partial acceptance tanks like in the middle where that bag wasn't the full size of the tank, a little less cost. But again, you didn't have the full acceptance volume of the tank with that. Now, the other thing I was thinking of along those lines.
Well, I'll jump in here too. You talk about these bag style tanks, and I know a lot of engineers like the serviceability of these bag style tanks and the fact that they are serviceable, especially on the ASME side. You can replace the bag and not have to replace the whole dang tank and everything like that. Getting those bags out of there is a lot like wrestling an alligator, and a lot of times you need like a block and tackle or some physical or mechanical means of actually getting it out of there. Yeah, and so. Don't think that they're necessarily the greatest thing sometimes, because most of the time they just get cut out and replaced anyways, but it's definitely something to consider, especially when you're looking for a full acceptance type situation. That would be a great source there, but just something to think about.
And then on the lower right, that's kind of a unique tank too. That's a potable water expansion tank, and it's a flow through, because there is some concern out there. If you have a tank on a dead end leg, is Legionella on your domestic waters? Is Legionella going to grow in there and then somehow get back into the system? So that's I believe it's a stainless steel tank too, that it is a flow through design, which is clever. And I've never used one, but I understand the the intent there. And then radiant specific, I think I said earlier, Amtro made a tank called a Radiant-R tank that was a line tank. So if you're on there non-barrier, I believe that's getting replaced by a newer version. Cody, did you talk?
Yeah, I think it was like the Xtrol Pro is what they call it, and it was a stainless nipple with a line tank and everything like that, so it could handle any oxygen ingress if you have a radiant system that is using non-barrier tubing or anything like that, where you could have excessive amounts of oxygen in there. So.
And I think it comes with that little indicator cap too as part of that new version. So,
Yep.
And then the different colors, are we doing a giveaway on why the colors are different or something? Is that?
I think that's a great idea, Bob. So yeah, we thought to ourselves, why on earth do they make them different colors? And we have a Coffee with Caleffi Yeti mug that we want to give away to you guys. So whoever comes up with the best answer in the questions pane as to why they are different colors, I would love to hear it. You know, this is pretty awesome. Along the same lines as far as bacterial growth and stuff like that, I've also seen a lot of these manufacturers that will actually advertise like a type of lining that will prevent bacterial growth as well. So there is a lot of consideration there. But like I said, I think the most important question we need to answer about this today is why they are different colors. Apparently it was what was on sale that day. They're supporting their favorite team. These are good ones. So keep them coming with that. Why are they different colors? I'd love to hear this. So like I said, we'll find the best one. We'll reach out to you, get you a mug there. Maybe Max could find the best one and let us know. So
now one of the other questions, Cody, and I don't know if there you go, if I put a slide in for it, but if I did, sorry, it's going to come up again. But somebody said, when do I have to go to an ASME tank? And I can't find an exact answer for that, even from the people that make the tanks. And so what I did is I just searched around a little bit. In some places, your state inspector, it could be a boiler code that's going to supersede the mechanical code. I did find online that Michigan and Ohio have 3 criteria. They say if it's over 210 degrees temperature, if it's over 200,000 BTU input, and if the tank is larger than 120 gallons, that's their 3 criteria for when you have to go to an ASME tank. And I don't know if that comes out of the boiler code or if that's just something they're comfortable with. Maybe that's a good rule of thumb, but I guess the bottom line is if an engineer designs a plan and he puts an ASME tank in there, that's what you want to use. If not, you can ask your inspector, your boiler code. I don't know where you're going to get an exact answer. And I think it could even come down to the actual inspector that shows up that day. He might have something in his head that says, oh, you know, it's 118 gallons. You got to have an, you know, I don't know. So I don't have an exact answer. You're going to have to check locally or check with an engineer in your area that does it for a living and knows what triggers an ASME requirement. And that comes up, Cody, I think with hydro separators all the time.
Oh,
too.
yeah. Yeah, we've got non-ASME like hydraulic and air and dirt separators and things like that go up to 5 or 6 inches. And it's really, I mean, you could flip a coin some days as far as when they're getting used versus when they're not. And a lot of it does have to do with the AHA in that particular area, and if they want an ASME tank or not, or for the Canadians, our friends north of the border, a CRN type tank. So
it adds a lot of cost because people say, well, you put a stamp on it and charging me a lot more money, but there's a lot involved with that. The steel, the nuts, the bolts, everything that goes into the installation that has to be recorded right back to the steel mill that made that bolt or nut steel or whatever. So there's paperwork involved. The welder has to be certified. So it's not somebody just putting a different label on that day and raising the price. There's a bit involved with any ASME vessel. So just know that compressor tanks, anything, they all fall under some pressurized vessel listing with ASME.
Yeah, and that's a great point, Bob. There was one of the questions where they asked, you know, what's the difference between non-ASME and ASME tanks? And a lot of it has to do with just a lot of the processes and steps that they have to go through to make those ASME tanks, whether it be the actual person doing it versus all the logging and you know, going all the information that they have to keep and record keeping in order to make that ASME tank. So.
And this slide just shows what we talked about previously with the 2 different styles of back type or bladder type. You can see partial and full acceptance there. So
yep.
The one on the right shows a removable one. You can see the bolted flange on the bottom, but I tried that on a well tank once, and like Cody said, better like a bulldozer there to pull them out because they don't come out very easily at all. Maybe it was old and stiff or something, but yeah, I wouldn't try that again for the cost.
Yeah, definitely not worth it. So.
Yeah, so the cap on the bottom, you know, as you can see in that one, it's got a Schrader valve like you would have under your tire stem in there that you can tighten it up and seal it off. So if you think the Schrader valve someday might leak out air, lose your air charge, tighten the cap when you're done. And there you can see the diaphragm. You can see there's kind of a, I don't know what you call that, a cinch ring or some kind of ring that locks that tank. That's what the one groove in there is. Locks that diaphragm in the tank. And I think as I read through the manual here, they really don't want you pushing that up much more than 50% of the way up the tank. Somebody can correct me if I'm wrong in there, because we don't want to stress that diaphragm in there. And if you did push it up near the top of the tank, if somebody under pressurized the air side, put more water in, then number one, you're going to stretch that diaphragm, but also you can reduce the acceptance volume of the tank because now your air bubble's been squished up in there. So two things, and we'll talk about that on chilled water and solar. There are some instances where you might want to overcharge your tank a little bit, which I think is coming up to give you a little reservoir. Okay.
Sorry about that. Let me kick that over there real quick.
So how do I size a tank? And there is a little different formula for compression tanks as opposed to a diaphragm type of tank. Both the formulas in there. You end up, you want to know what the fluid is. Is it water? Is it glycol over percentage? The minimum pressure that you're going to fill the system, your static fill pressure, the maximum pressure that you can run that at. Usually we figure, I think it's coming up on a slide, 27 PSI on a system that has a 30-pound release valve. And then the temperature differential from when you fill it, let's say 55-degree water coming into whatever it's going to go up to 200 degrees. The volume, the trickiest number to get when you go into these sizers is the volume. If you've got an engineered drawing and it was put in exactly like that, maybe through his software, he's got a fluid capacity number on that system. But if it's a troubleshooting job or replacement or the building has changed over the years, it's really a guesstimate on how many, especially on large buildings that could hold, 1,000 gallons of fluid or more. So, you could err on the, and I think some of the quick sizers where it just says how big is your boiler and gives you a tank, I would say there's probably some wiggle room in those sizer calculations. So what you'll find is if you want to use one of the online calculators, if you use click on the commercial one, it lets you put in more of this information than just the residential. It just says what size is your boiler, kind of in the temperature range, and gives you a choice. So this is an option of using 2 expansion tanks instead of 1. They'd both have to be pre-charged properly. The do's and don'ts in this picture right here, classic example of that tank on the left side of the picture, doesn't have very good support other than the threads on that nipple, and that looks like a number 60, so that's going to weigh 90 pounds when it's waterlogged. So I doubt that pipe nipple is going to be up to that task. So
yeah, this is a perfect example of when that sheet metal screw might come into play. If that thing's all waterlogged, then you don't really feel like taking a bath that day. So
also, what I would point out with the camel pump air separator in there probably isn't doing much work, because you really want to have about 18 inches of straight pipe in front of that so that water can slow down. So I had one of the contractors at one of my seminars tell me, he said, well, that's just a coupling. He said, that's not an air separator. Convenience
it's a really heavy coupling. Yeah.
Maybe it's a cross fitting instead of a coupling, but that was a good point. They're not doing what you think they're doing. So.
Yeah, good place to hang your expansion tank there. But yeah, for sure.
Exactly. And there's
sure following the rules.
On the bottom, we do sell a package. Like Cody said, we don't make that tank, but we sell it with the nice thing about ours, it has brass nipples and everything on it too, so you don't have to worry about corrosion there.
Oh, yeah. For smaller residential size type stuff, we sell a kit. Basically includes like the air separator, the expansion tank, and all the fittings, fill valve, and backflow preventer, and everything like that. So make sure to check those out too.
So as I just showed on the previous slide, we want to go, okay, what is our minimum pressure that I pre-charge my tank to? Well, you need to know what the pressure of your system has to be to get 5 pounds of pressure at the highest point in your system. We always want 5 pounds positive pressure at the top of the system. So if I do have an air vent, that one I guess is just manual bleeders, but when I open that, I'd like to have some pressure there to push the air out. So we say take the highest point in the system above the tank times 0.433. That gives you the fill pressure to get water up to the highest point. And then they add 5 pounds to that number. So as you can see here, we've got a system that's called, 12 PSI on a 2-story house. Typically, that's going to give you enough. But that's what you need to know is that 0.433. And you can guesstimate that. If you round that number up to 0.5, and you take the height of the building, it's just half of that. So if you got a 40-foot tall building, 20 psi, gives you a little bit of wiggle room and makes the math so you can do it in your head. So now you got to charge your tank. Before you put your tank onto the system, you want to put your air gauge on the bottom and make sure that it is set at that number that you came up with, that let's call it 12 plus 5, 17 maybe on this system. And know that the tank might say pre-charged to 12 or 15 on some of them. I wouldn't bet the farm on that. You know, just because somebody put that in at the factory doesn't mean when it gets to you, it still has that exact number. So get an accurate, like a bicycle or an ATV gauge that's a low pressure gauge that you can get a good accurate reading on that, especially if you're looking for a 1 to 2 pound range there. You don't want to put a 100 PSI pencil gauge on it and have it say, yeah, you know, either 10 or 20. It doesn't get you accurately, an accurate enough number. Okay.
All righty. Yeah, and you mentioned before too, Bob, you know, as far as the half PSI, that works for most of your smaller, you know, smaller buildings and stuff like that in hydronic systems. Anytime you get into the larger buildings and stuff, you need to be a little more accurate, you know, especially, you know, when you get, if you are using residential boilers with 30 PSI reliefs and stuff like that, you know, you get into those 4 and 5 story buildings, you're cutting it pretty close sometimes. So you got to make sure your math is on the nose there. So.
Yeah, and if you're talking like a multi-story, you know, high-rise building, obviously that number goes out the window, and you're probably not running those at 30 psi anyways. And there's some tricks you can do on those buildings, which again I learned reading through the Amtro book. The tank could go up somewhere higher in the building. The tank doesn't have to be at the boiler, so that's another way you can work around a tall building. And yeah, so yeah, here we came up with, we would suggest 27 psi. You know, I know the relief valves. A relief valve that's rated at 30 psi, my understanding is it should be able to go up to 30 and then start to weep or trickle a little bit. It's not going to pop full off at 30 psi. So if you stay at 27, you're below that threshold where you start to, you know, maybe get a little seeping, assuming that it's made that accurately with the spring tension.
Yep.
How are we doing for time? We're looking pretty good.
We're doing pretty good here, yeah. Just a quick question for the questions pane there. Should you trust the pre-charge pressure of an expansion tank? We're seeing a resounding no from everybody that's jumping in there. Like Bob mentioned before, definitely check the expansion tank. Make sure you got a good gauge on there to get an accurate reading on that one, especially a lower range on the gauge, so you get a little bit more definition. Don't check it with a 0 to 100 pound gauge, because you're not going to be able to get it as close as you need to. So yeah, so some great answers in there. I appreciate that. But anywho, all right, so yeah, let's talk about the pre-charge pressure. You know, what pressure should I set that tank to versus, you know, what the pressure is in your hydronic or your potable system?
Yeah, so like we talked about the fill pressure, the math is in there if you want to get, so what you do is if you use that formula there, you'll come up with what's called the acceptance factor. And then that's the factor, if you're doing bigger systems, that you get to size, you know, compression tank or any tank. If you want to do the math, again, the quick calculators, which will show you coming up, will be in there. Now, there are some conditions, and it's probably going to be getting in the next slides, where we might want to have a little bit of fluid in that tank when we charge it, that we might want to keep the air pressure maybe a pound or two below what we're going to fill the pressure, so that when we fill it, a little bit of fluid will go in that tank. And I think Wiesman calls that a safety seal. You got a little bit of water, so if there's a condition in your system where the pressure could drop below what you filled it at the day you filled it, you got a little bit of fluid in there, so your gauge is going to drop to 0. If you got a leak in your system, you start flipping out because your gauge went down to 0. And where that's going to happen, and the slide will be coming up, is a solar thermal system. But let's say that since this is coming up next. So yeah, so these are the expansions, and every manufacturer has one of these. What I did see on the Wessel site today is they actually have a compression conversion calculator. So if you put in the size of your 30-gallon compression tank, it'll give you, and then input all this information, the temperature and the pressures, it'll give you the conversion to the a diaphragm type. I was going there thinking I'd find one the size of compression tank with a calculator, and it's a conversion, not a sizer, but I think there are some, you know, plain steel tank compression ones. If not, the book goes through the factors that you need to use to get that. And the interesting thing about the one example I talked about in the Amtro book, where that 7,000 gallon system, here was something that blew my mind. I think it was like a 1,200 gallon compression tank was going to be required, and like a 60 gallon diaphragm type tank for the same system. But the thing that really blew my mind is the tank that was required on a plain steel tank was 14,000 pounds of weight between the weight of the tank and the water that would be in that tank. And the other one was 700 gallons. So not only do you have a much bigger tank somewhere in your building, you got to have the structure to be able to put that somewhere to support 14,000 pounds, about 7 ton, right, of tank and water and that. So that was kind of interesting. And another interesting thing in there, it tells you even how much that tank is going to expand as you take it from 55 degrees to 180 degrees, and the volume of the tank increases because the jack at the wall of the tank actually increases, and it was like 8 gallons or something. This tank is going to expand, which again should go into the formula as your volume in your tank, I guess. So
I'm going to back up a couple slides here. We had a good question here about explaining again the minimum and maximum operating pressure again in these systems. And we talked about it before. When you're setting your fill pressure in your systems, on hydronic systems especially, you want to make sure that you have at least a positive pressure of 5 psi at the top. So that should be theoretically your minimum pressure, is to make sure you can at least maintain a 5 psi positive at the top. That makes sure that all of your air vents are going to work properly. The pressure will push the air out of there. It'll also make sure that when the system all turns on, that those air vents, which are really good at letting air out, it's going to make sure that those air vents aren't letting air back in, because they're also really good at that too. Okay, so you want to make sure you're keeping the air out of the system, pushing it out with that 5 psi. Now, as far as your maximum operating pressure, it really has a lot to do with what your pressure relief valve is set to. If you want to keep it pretty tight, making sure that expansion tank is sized properly, but there might be some scenarios where you can get away with a slightly smaller expansion tank and you're just going to have a little bit more pressure increase in your system. And as long as it's okay, then knock yourself out kind of thing. I don't know if you have any thoughts on that, Bob.
No, that's exactly it. I mean, whatever you're willing to accept before your relief valve, or whatever the pressure rating on your boiler is. Most of them are 30 pounds. Some of the commercial boilers, or even some of the residentials, this one behind me will allow you to go up to 45 psi pressure relief valve. But that's, again, you put that into the formula here, what your pressure, acceptable pressure range is, and your temperature swing, and that one just shows water. And the reason I put this one in is on the next slide. I think, Cody, I show it with glycol. It makes a big difference. So you'll see on this one here, I put
50% glycol.
And I don't know if you recognize those tanks, but the tank size went up quite a bit by just adding glycol to that same system with the same, temperature and pressure criteria. So I'm not a big fan of glycol unless you have a freeze protection. It brings a lot of baggage. Your expansion tank, your pump sizing changes. It's really tough to get air out of glycol. A solar guy called me this morning. He's got foam in his solar system. I said, well, you're probably stagnant. You're probably 300 degrees up on that collector, and you turn that pump on, and now you got foam coming out of your air vents. So you got a couple things going on there. But yeah, I mean, it's just know that you got to size everything in relation to the percentage of that glycol and the temperature swing. So
yep, for sure. All right, now we talked a lot about hydronics. What about potable side here, Bob?
Yeah, so basically all the same rules apply, how much volume you have to accept in your expansion. There's quick sizers for these also. It's going to be a line tank. I think that tank has a stainless steel nipple on the top instead of a steel nipple, obviously. On the right there, that can be used for tankless water heaters that only hold a little bit of volume. Now, Cody and I talked about this yesterday. He said, you know what? Some of these new tankless water heaters have tanks in them now. I saw one brand has, I think, a 10 or 12 gallon tank inside the tankless water heater. Well, you got to start paying attention to that, because now maybe that little softball on the side there, that little domestic water expansion tank for tankless things, might not have the capacity to do that. And one of the pre-submitted questions, if you have a bank of these tankless water heaters, yeah, you still got to be able to accept the expansion of that. And at the last HR show, I saw, I think it was Renai brand, hanging on the side of a 50-gallon tank. So a tankless water heater on a 50-gallon tank, you kind of have a tank water heater, so you got to size your expansion for that whole thing, not just for that little tankless water heater capacity. So anything else?
Yeah, the other thing I'll bring up too is, a lot of guys, expansion tanks might be code in your area for the contractors and for the engineers. The other big one that a lot of people don't really think about is anytime you have a closed system on your potable side, and meaning a closed system that, all the faucets are off and you have like a backflow preventer in there. That's a closed system. Then at that point, if all the fixtures are off, you need to be able to accommodate for any temperature increase or decrease with an expansion tank like this. Okay, now from there though, one thing that a lot of people don't consider is sometimes in your area you might not require a backflow, but you require a pressure reducing valve. And a pressure reducing valve, ironically and inadvertently, does almost the exact same thing as a backflow preventer by allowing water through it, but not backwards, okay? And so the big thing there is if you do have a pressure reducing valve, you've got to make sure that you have an expansion tank on there too, to make sure that you can accommodate that expansion even without a backflow preventer. So
these tanks will typically have a 3/4 connection on the top instead of half, so that's how you can recognize them different from a thermal expansion. I have heard of guys using these on hydronic systems, just lower the pressure, of course, because these are typically 45 or 50 PSI pre-charge. I believe the bladders are pretty similar, that it could be used if you want to, and now you got a line tank again, but since they make a radiant or a hydronic specific line tank, I would go that direction. All right. Yeah, so here we go with the chilled water system. So same thing, the pressure is going to be based on the fill pressure at the lowest temperature. Now, if you're filling this thing at maybe it's 70-degree water coming into your house, or in Phoenix and the water comes in at 80 degrees, you got to know that that water is going to, you know, contract as you cool it down to 55 degrees or whatever you're going to chill that water to. So we got to be able to accommodate that temperature swing as we chill the water also. So yeah, so the time you're filling it, the temperature there, and then what else do I have? It must be filled to higher pressure. So this is a case where if I'm filling it with, let's say, 70-degree water, and I fire that thing up and I've got a pre-charge and I've got it set at my fill pressure and I cool that water down, the pressure is going to drop. And the expansion tank, if you had a little bit of fluid in it as you pre-charge it, now you've got a little bit of buffer so we don't see that gauge dropping down to zero. And it can go worse than that in this example here. And I don't, maybe I should read this since it is so important. The bottom part is important. As the water cools below the room temperature, the diaphragm can go down against that expansion tank, and now you could pull a subatmospheric condition, pull a vacuum in your system out there. And as Cody said, now if you've got an air vent somewhere in that system, a little float type, float's going to go down, air is going to go in there, and you're going to start airlocking your system because you've pulled a subatmospheric condition and you're allowing air to go into your system. So that's why you want to have that little bit of extra capacity in there as we know the temperature is going to drop below what your fill water temperature is. And it gets even a little bit more complicated with solar, because the same thing will happen in a solar. Let's say you fill the solar system with 50-degree water. Turn the system on for the first time, and it's a sunny day, warm summer day like today. I might get up to 170, 180 degrees out of that collector by the time it heats up at the end of the day. In the wintertime, I could have that temperature of that collector be 0 degrees. So now I filled it with 55-degree water, and now I got 0-degree temperature in that collector. Now I'm going to see a decrease in pressure on that gauge, and you're going to get a phone call. You got to come out here. I got a leak in my solar system somewhere. My gauge dropped down to 0. And where it gets even a little bit more complicated when you start sizing, which is why the formula gets kind of big over there on the right for solar thermal, is think about a solar thermal system when it goes in a stagnation condition. And what I mean by that is the pump goes off for whatever reason. Maybe the tank got up to temperature, maybe the controller failed, the pump jammed up, whatever. And now you got a collector up there going up well over 300 degrees. I think we calculated on a flat plate collector somewhere around a 344-degree stagnation temperature on a full sun day. What's important to know there is that temperature is probably only going to be seen at the collector and some of the piping. So I don't want to size my expansion tank to handle from 0 degrees to 344 degrees. So what this formula will allow you to do is subtract out the volume of the fluid that's in the collector and in the piping that could be exposed to that temperature, and back that out of the formula so I don't have to try and accommodate a 344-degree temperature differential, essentially from a wintertime 0-degree temperature at a collector to a stagnation temperature condition up there. And so basically what you're going to see on when we do a sizer here, you'll see that we really oversize that expansion tank. You say, gosh, I got a pretty big tank for a system that only holds 8 gallons of water. Well, number one, we want to put a little bit of water in there, so we need a bigger tank so we have enough acceptance, but we've got that little seal of water in there. We overpressurize a little bit so our gauge doesn't drop at cool conditions. Also on those temperature evacuated tube systems especially, they do make a tank that you could put between your expansion tank and your piping that's actually, oh, there it is, I put it in there. That little tank is a cool down vessel. It's intended to take that high temperature, that shot of glycol that's coming out of that collector at maybe 300 degrees, and maybe cool it off a little bit before it gets into the diaphragm. The solar ones typically have a higher temperature diaphragm, certainly not 300-degree temperature, but that's one way. I've seen people even on in the MTRL book on some of these bigger systems, they show a piece of fin tube on the line between the, the boiler, the solar, and the tank to just dissipate some of that heat, so we're not shocking that tank with that super high temperature. That happens to be a Zilmit brand, that intermediate vessel there. We've got 2 minutes. I think we're close to the end here.
Yeah, we're pretty close here, Bob.
Yeah, so there's on my garage floor, just some of the tanks I got kicking around. You'll see a solar tank there. I think that blue one's actually a well tank that goes on a little pressure booster. A pancake type of tank there, and that red one. There's some round, flat ones if you want something for the guys doing the diamond plate wall that want the look of a round tank or a pancake tank. Those are available. What else?
Yeah, we talked about the different mounting options, the different types of tanks. We talked about how to size them, which really has a lot to do with the volume of water in the system, the temperature variations that the system is going to run into, and what your minimum and maximum requirements are for whatever system you're working on to make sure you can get that thing sized appropriately. We talked about chilled water, solar, talked about some potable water application tips as well. Yeah, there's a lot of information, and like Bob mentioned, that particular engineering handbook from Amtrol has a ton of good information in there, so definitely check that out. Anything else you want to add there, Bob?
I would say, if you have a question, we can help you. Certainly the people that rep these tanks, some of our reps I think are on today,
Yep.
that rep all of the brands of the tanks. I mean, that's what they're there for, to help you with sizing information, troubleshooting information. If you want to switch from a compression tank to another tank, or vice versa, if for some reason you want to put a compression tank in the system, you need to know how to size that. That's what they're paid to do, and that's what they can help you do. And they probably have some tips on what we put out there today and some of the stuff. But yeah, so we'll answer any questions that came in, and ones that we can't get to at the time we want to go over here a little bit, or I'll answer via email or something like that, so you can make sure that we got everything. I tried to build as many of the pre-submitted ones into here as I could, but I know there were some of them that I didn't get to, or that might have come in that our support team there might have been answering as we went through here. So do we have time to do a couple of questions? At what, a minute?
Yeah, I think we do. We got a couple of questions. Max, are you on? Have you been keeping an eye on the questions? One thing I wanted to touch base on real quick is for those of you that don't trust the pressures in the expansion tanks on the air side when they get delivered to you, those were actually packaged and assembled by, I believe it was Tom Brady. That's that part of that whole Deflategate scandal and everything that happened a few years back. That was pointed out to me in the questions pane. So I appreciate that little number there, but Max, are you there?
I'll throw in that somebody's asked me over the years is they said, are the tanks charged with nitrogen? And I heard at one point they were, because nitrogen doesn't go through the bladder as quickly as, just air that charge. What I did learn from Roger, who used to work for Amtrol, is that they did use refrigerated air. And by using refrigerated air, you pull the humidity out of it so they don't have humidity in the tank. But I don't have any confirmation that they were charged with nitrogen. I guess you could, Cody, if you have a nitrogen tank on your, just like the tires on your vehicle, some people,
yep,
if you see the green caps on them, they've been charged with nitrogen. Some people say they don't lose pressure, and I guess that's true if you look at it from a scientific standpoint. But if anybody from Amtrol or anybody tuned in today knows about the nitrogen versus refrigerated air versus just my compressor, let us know.
No, that's a great point with nitrogen. If as a contractor, if you're doing refrigeration or AC work or anything like that, I mean, you've got a nitro tank already on your truck. I mean, knock yourself out if you wanted to bleed it out and put some nitro in there.
Don't take it right out of the tank into the expansion tank. Have a good regulator.
Yeah, for sure. All right. But yeah, it looks like some people were asking about that Amtrol handbook. We'll see if we can find a link to that for some of these guys. Yep, Bob's got the copy of it right there.
And I saw not only, like you say, if there's a link to it, but you can buy it from people that do PDFs of all sorts of code books. I think you have to pay for it, but I found 3 or 4 different places online today that it's in a PDF. I didn't check and see if you had to pay for it. It's some of the, what are those companies called that, they scan all the different code books and all the different manuals and like CAR idea. There's a couple different out there, but I would go to Amtro first or REP. Number one, you might have one if you like I do, because I make all sorts of notes inside of mine. Ask your rep first if you want a hard copy, but we'll find out where you can download it or link to it somehow.
Yeah, there was one question in here, and I think this is a great one. Is there any downside of using a potable tank for hydronic systems rather than a hydronic specific tank? And I think the big thing there is, one, the difference is that the potable is going to be a line tank, so that way you don't have access directly to the steel inside those tanks. The other big one is that the pre-charge is going to be a lot higher in a potable tank versus a hydronic tank, so make sure you're checking on that. The other big difference is the connection size, usually 1/2 inch versus 3/4. Anything else that you can think of, Bob? Any other downsides there?
I did look at that today. I looked at the two different tanks, and one says it's got an EPDM diaphragm and the other one says butyl EPDM. So I don't know if the bladders are changed from one to the other. Again, that would be a manufacturer specific question. I would think it's the same material used in both of them, but you would want to make sure if you did use it on a hydronic system that the bladder can handle not only water, but glycol or any chemicals that you might put in there. But I think the butyl EPDM is, pump gaskets, a lot of things are made out of EPDM. That seems to be the go-to material for seals and hydronics, but I'm not sure. And like I said, some of them now are saying they've got an antimicrobial. I don't know if that's
antimicrobial, I think is the fancy term there.
Yeah, and I don't know if that's built into the bladder or where that is in the tank, but I don't want to give you bad advice and say, yeah, it's fine to do that. I would check with whatever brand tank that you're going to do, but I know people have used them on non-buried tube systems and get better results than the plain steel.
For sure. All right, well, guys, I think we got all the questions there. There was a few more there. Some of them get a little more specific in the question span. We really appreciate those questions, but we need to make sure that we get through this in less than a few hours usually. So if there are any questions we didn't answer from the questions box, we'll definitely get back to you on that one. We'll go through the end slides here, just kind of go over some of the things that might be helpful to you guys. If you guys have any questions, don't hesitate to contact us at Caleffi. We've got a great team for tech support in Milwaukee here. We'd be willing to help you with anything you got going on hydronic or potable. If you're looking for more information and more resources, we've got a podcast with Greg and Dan talking about kind of the day in, day out stuff that they work with on a regular basis. So check that out. We also do a mini training series. I actually do a mini training series called 5 Things You Need to Know. So we talk about different applications, whether it be why your pressure reducing valve is making a lot of noise, or Legionella in potable distribution type systems and things like that. So check that out, 5 Things You Need to Know on YouTube. From there, we're also on all of the social media sites, so check that out, especially for the contractors out there. They seem to love Instagram quite a bit there, so we do actually do quite a bit of stuff on Instagram. We always like to see your installation shots there too, so check us out on all the different social medias. And you guys, thank you so much for your time. We had a great attendance today, and if there are any questions, don't hesitate to reach out. And for those of you that didn't get your question answered, we'll be back in touch with you. And you guys enjoy the rest of your day and your weekend.
Yeah, thanks everybody.
Thanks, Bob. We'll see you guys.
Hey, Cody.